is fairly simple in principle. The idea of secure boot is that the firmware, in UEFI, is the firmware that is responsible for starting applications. The firmware will only start applications or binaries that have an appropriate and trusted signature. Now, anyone can sign a binary if they produce a key, but the platform will only trust keys that are specifically enrolled in the firmware. So if you sign a binary with a key that is not trusted by the firmware, then that binary will fail to start as if it were not signed. And the problem we have here is that due to Microsoft requirements that any machine with a Windows 8 hardware certification must have Secure Boot enabled by default. And once Secure Boot is enabled, it is not straightforward for the end user to either disable it or to change the keys, which means that the keys that ship with a machine, the keys that most people will have, are controlled by the platform vendor, by the OEM, and not, in many cases, by the customer. So, in a traditional boot environment, this is what you see. You have the firmware, and then the firmware starts the bootloader, and then the bootloader starts the operating system. And this is all very straightforward. This is as you would expect. Here, with the colors, the blue here indicates that all of these components are good. All of these components are as they should be. They're all trusted. Now, there's a problem with this, and the problem is that we're seeing a change in the way that malware authors attack operating systems. And it used to be that if you wrote a virus, it would just run under the operating system. Now the problem is that these days, antivirus checkers tend to be very deeply integrated into the operating system, which has made it much more difficult for the malware authors to run their viruses and their worms in the operating system. So instead, what's beginning to happen is this. We see attackers who are able to exploit a vulnerability in the operating system. Then, instead of putting their attack components in the operating system, they put the attack component between the firmware and the bootloader. They tell the firmware to run their malware, and their malware then loads the bootloader, and then the bootloader loads the operating system. This is happening in the real world. There are still a fairly small number, but there do exist viruses and worms that do this. In some cases, one of them even installs itself into the BIOS. So if a system has the hard drive replaced, it can reinfect the hard drive from the system BIOS. And once you have executed untrusted code, that untrusted code can then modify everything that comes after it. It can load the bootloader. And for instance, if you imagine that the bootloader may verify that the rest of the operating system is good, if you are the one loading the bootloader, you can load the bootloader and then modify the bootloader so that the modified bootloader, in turn, modifies the rest of the operating system. And once you can no longer trust the operating system, it's impossible for you to detect that this has happened, because if you attempt to ask the content, if you attempt to read the contents of the hard drive, if you attempt to validate that your bootloader is good and unmodified, then the malware can modify your operating system to give you back the answer you're looking for. It can lie to you. Once you've executed this untrusted code, everything from then on is untrusted. And that means that you have to assume that an attacker knows all your passwords, that an attacker knows all your credit card details, that an attacker can read your keystrokes, that an attacker can execute arbitrary code whenever they want to. If somebody can load this malware before the bootloader starts, then everything is untrusted. So in secure boot, if somebody inserts malware and tells the operating system to boot the malware, then the firmware will attempt to load the malware and will find that it is unsigned, or that it is signed with an untrusted key, or that the signature does not match the binary. And it will then not execute it. It will load it, verify it, and then refuse to start it. And instead, depending on configuration, it may then attempt to load something else, or it may fall back to a remediation state. It will bring up an error saying that it was unable to boot the operating system, and then launch a verification application that will ensure that all the system components are unmodified and can potentially remove the malware. Secure boot is designed to stop this attack, and this attack does genuinely exist, so secure boot is attempting to solve a real problem. But obviously there are some difficulties involved with it. When we say that it will not boot malware, it can't boot malware because it doesn't trust the malware. But how do you define trusted software when you're talking about, say, Linux, when you're talking about software that is produced by thousands, if not millions of people around the world, software that anyone can modify? Because if somebody receives a copy of Linux on the CD, that could have come from hundreds, if not thousands, of different distributions, and each of those will be different. There's no way for the firmware to know which of those are good. And the other risk is that even if you do trust a Linux bootloader, how do you then trust the rest of what you're going to boot? Say you load a bootloader that then loads a kernel, then that kernel may, well, if the kernel is not also trusted, then that kernel could instead be a piece of malware. So an attacker could take a signed Linux bootloader, and if that signed Linux bootloader launched an unsigned kernel, the attacker could replace the unsigned kernel with malware, and we're back to the original case, except it's worse because now the firmware will load the signed bootloader and will load the malware, and it will believe that everything is okay. So we have to attempt to come up with a solution for identifying how to produce a signed version of Linux that does not then immediately permit malware to be reinstalled into the systems. So this is an overview of how secure boot works. You take your binary, your message, you see in the top left, and you generate a cryptographic hash of it. Now, according to the UEFI specification, there's a whole range of these, including MD5. Now, one of the wonderful things about UEFI is that the specification is around 2,000 pages long. The specification defines a large number of things, and many of these things are not implemented by any version of UEFI you can buy. So the specification says that you can use MD5 as your hashing algorithm, but nothing will accept MD5. In reality, the hashing algorithm has to be either SHA-1 or SHA-256. And in most cases, it will be SHA-256. So you take a cryptographic hash of your binary, and then you encrypt that hash with a signing key. Again, in theory, there are many different types of signing algorithm. In reality, it's 2048-bit RSA. So you encrypt the hash, and then you put the hash into a header in the binary. Now, when you come to execute the binary, the firmware calculates the hash of the binary itself, and so it now has a comparison hash. It then attempts to decrypt the encrypted hash. If it doesn't have a trusted key, then it will be unable to decrypt the hash, and the verification will fail, and it will refuse to launch your executable. If it can decrypt it, it now has a decrypted hash, and it checks that decrypted hash against the hash it calculated. And if they're both the same, then it knows that the binary hasn't been modified. Because the combination of these two things means that it knows that it was signed with a trusted key, and it knows that this signature came from this binary, this unmodified binary. And then it knows, well, I trust the owner of this key to produce software that isn't malware, to produce trusted software. And I believe that this binary came from them. So it will then execute the signed binary. And if you modify the software, then that won't work. If you change the signing key, then that won't work. So it's not possible to just take a piece of signed software and modify it and still have the signature validated. So in principle, assuming that there are no bugs in the implementation, which may be a big assumption, this is completely secure. There is no way to get around this. Now, when I said the trusted keys, there's actually multiple different types of key in secure boot. There's what we call the platform key, and the platform key is the most important key in the system. The platform key is typically owned by the system vendor or by the OEM. Now, that platform key is the last key that's installed. Once the platform key is installed, it is not possible to perform any further modification of the keys unless you have a key that, unless you already have one of the keys. The holder of the platform key can update any key they want to. They can provide updates that are signed with the platform key and which allow them to replace any key, including the platform key. So the platform owner can change the platform key if they want to. They can push out an update and the firmware will accept that update and the platform key will be changed. Below the platform key you have the key exchange keys. A system may have one of these or it may have more than one of these. The number is limited only by the amount of storage space you have for variables. Key exchange key is intended, well, it was envisaged by the specification that the key exchange keys would be owned by the operating system vendors. So, for example, Microsoft will have a KEK on any system that you purchase that's intended to run Windows. The KEK allows you to encrypt updates that allow you to add new entries to DB or to DBX. A DB is the list of keys that are trusted for signing binaries. If you attempt to execute a binary and that binary is signed with a key that's in DB, then it will execute successfully. If the key is not in DB, it will fail. There's also DBX. Now, DBX is like DB, except if your key is in DBX, you will not execute, even if your key is also in DB. DBX means that anyone with a KEK can provide revocation updates. If a binary is signed with a key, and then that key is leaked, then anyone would be able to get that key and would be able to sign malware, and we'd be back to the original problem. So to deal with that, that key can be added to DBX, and from that point on, that key is useless. That key has been completely blacklisted. It's also possible to blacklist individual hashes. So if you sign a binary that turns out to have a security vulnerability, which can be used to execute arbitrary code, which again would allow you to avoid the signing requirements, then you can simply put that hash in DBX. You still trust the key. The key is still held by people that you trust, but you want to stop this specific binary from being executed. So you add the hash to DBX. If anybody attempts to execute that binary, then it will fail. It will not boot. Per the Microsoft requirements, there must be at least 64 kilobytes of space available for variable storage and a minimum size of 32 kilobytes for each of these, which means we can effectively have up to 32 kilobytes of revoked keys and hashes, which means a lot of hashes, a lot of keys can be revoked. And there's probably not going to be a situation in which we run out of space to store blacklist updates. But the question then is, well, we've said that the platform vendor normally owns key K, but who owns the rest of the keys? And this is where things start becoming more difficult. I'm using HP as an example here. It could be any vendor. It could be Dell. It could be Shuffle. It could be Samsung. It really does not matter. The platform key will generally be held by the platform vendor. Below that, we'll have the KEK. And the KEK will obviously have a Microsoft entry because Microsoft want to be able to provide security updates for blacklists. Microsoft do not want to have to go to every platform vendor in order to get the platform vendor to provide security updates. Microsoft want to be able to add to the blacklist themselves. And we could also imagine that the platform vendor will have a key in KEK, which then allows the platform vendor to themselves add new entries. And you might wonder why the platform vendor would want new entries. And the reason for that is because the platform vendor will themselves have some tools that are assigned. The platform vendor may have diagnostic tools that they wish to run on their system. And it would not be particularly useful if the firmware refused to run the vendor's diagnostic tools. So we would usually expect that to be signed with a vendor key, and so we'll have a vendor KEK so that the vendor can update that, and so that the vendor can blacklist their binaries if they need to. If they pushed out a diagnostic tool that has a security vulnerability, then again that can be used to attack their systems. So they also need to be able to blacklist keys. And then in DB, we would have the vendor key in order to allow the vendor binaries to be executed, and we would have the Microsoft key in order to allow Windows to be executed. And that's great. You can run any tools that came from the platform vendor, and you can run Windows, and you can't run Linux. And this is unfortunate for us, because if you can't run Linux, then we can't sell you anything. And if we can't sell you anything, then I have to find a new job. And I don't think my new job would be as much fun as this one. That would make me sad. So perhaps we could have a Linux key, and then we would add a Linux KEK, we would add a Linux entry to DB, and then we would have the ability to run Linux. The problem here is when we say a Linux key, who would have that key? You need a company or an entity, some sort of organization, who would take responsibility for ensuring the security of this key. Because if this key got leaked, then malware could be signed with it, and then that malware would run on any system that had the Linux key. You would need to be able to verify that people who came to you and said, I have this Linux distribution and I would like my key signed, you would have to verify who they were. You would have to make sure that they are really a Linux developer and that they are not a malware developer. You would also need to, for instance, make sure that they're not the US government, who would perhaps want to run software on people's computers in order to spy on them. And doing that is very expensive. We're talking millions of dollars per year. And setting this up in a way that allows it to be audited, setting it up to make sure that it is secure, that all the processes are trusted, that would take a long time. And nobody has volunteered to do this. You might think, for instance, that the Linux Foundation would be a natural choice, but then the Linux Foundation last year had all their websites broken into. And so it's difficult to convince hardware manufacturers that the Linux Foundation is a trustworthy security provider. So while this seems like the easiest and most natural approach, we couldn't really find anyone who was willing to do this. And if we couldn't find anyone willing to do this, we couldn't go to hardware vendors and ask them to take the key, because we didn't have a key to give them. I should emphasize here that all the hardware vendors we spoke to were very happy with this idea. Even Microsoft did not have any objections to there being a Linux key. The only reason that we don't have a Linux key is that we haven't found anyone who could do that job. It's not a conspiracy that has resulted in there being no Linux key. It's just we don't have one. So how about another approach? We could have a Red Hat key. Our Red Hat is a company that I trust. I work for them. So they keep giving me money. I have to trust them. And if we had a Red Hat KEK and a Red Hat entry in DB, then obviously Red Hat would boot. And that's great. Except Ubuntu wouldn't. And while that would not cause me any problems, I think there are some people sitting in this room who would be quite unhappy about that scenario. So this, again, is not a particularly good answer. We could add vendor keys, but then, okay, we add the Ubuntu key here, and then SUSE doesn't boot. So we have the SUSE key, and then Mint doesn't boot, or Mageia doesn't boot, or Debian doesn't boot. And so we add those keys, and we keep adding more and more keys. And every time we add a key, we're saying we trust these people to be secure. And some of them aren't going to be. Some of them are going to be better at being secure than others. And every time one of them is insecure, we have to work out how to blacklist their key. And if they have a KEK entry, you can't blacklist them. The only ones you can blacklist are the DB keys. So if we gave a KEK out to a company or out to a Linux distribution, and if that were then installed on every machine sold, then if that key leaks, secure boot would be destroyed. All of those computers would be vulnerable, and there would be no way to revoke that key.
Somebody should do it.
So perhaps somebody should do that. Well, yeah. The problem then is that the next generation of machines would have those keys missing, and it would then be much more difficult for us to convince the hardware vendors to add the keys again. There is no centralized authority. You can't go to someone and say, here is my key, put this in all UEFI systems. You have to go to, if you're lucky, you can just go to the firmware vendors. You can go to Phoenix and AMI and Inside, and you can say, well, please include these keys, and maybe they will. But then some of the hardware vendors may say, well, this takes an extra 3 kilobytes of flash, and that costs us 2 cents per computer. So we don't want all of these keys, because we want those 2 cents instead. And that, then they may remove all the keys except for the most popular Linux distributions. And that is not a particularly good answer either, because one of the great advantages of Linux is that you can start from nowhere and become popular. Remember, Ubuntu is less than 10 years old, and is now the most popular Linux distribution worldwide by a long way. If it weren't possible to have your key added to a system until you'd already become popular, then we will never have a new Linux distribution. So we mostly felt that this was not a solution, that this had too many drawbacks, that if we went for one key per distribution, then there would be too many distributions that wouldn't work. And you would risk a scenario where some computers might have the Red Hat key, but not the SUSE key. And some computers might have the SUSE key and not the Red Hat key. And computers sold in America might have the Red Hat key. Computers sold in Germany might have the SUSE key. And you wouldn't know which Linux you could install on your system until after you bought the system, potentially. Or you would have to check lists. Or it could be that the same computer sold in different countries would have different keys. And if you want to run SUSE, you might have to go to Germany to buy a laptop. We really did not like that approach. So we ended up taking a controversial decision. And when I say we here, I mean Fedora. Sorry, did you have a question?
May I ask, who else will be hurt except the user if they don't have this system?
If you don't have the key, or if you don't have the right. So
if you don't have this security system.
Okay, so Secure Boot is required by Microsoft's Windows 8 certification. if you want to have the Windows 8 logo on your hardware, then you have to have this system installed. Now, if you're a big hardware manufacturer, you want that logo, because that means that you get Microsoft marketing, it means that you get preferential treatment for Microsoft licensing. Having this means that your profit margin goes up. So since most companies are just selling to the Windows market primarily, they want the best profit margin possible. If Dell chose not to do this, then Dell's profit margin would be cut compared to HP. HP would be able to sell cheaper computers, and HP would then sell more computers. So everyone who sells into the Windows market will, everyone who sells into the Windows market will be using this. If you're producing hardware specifically for Linux, you don't have to do this. And you could be fine. There is the risk that at some point somebody will start attacking Linux with rootkit malware in the same way that people are attacking Windows. But right now they're not. So you could almost certainly get away with just not implementing this feature at all.
Is the ME related to this? I mean, Intel?
The Intel management engine?
Yeah.
No, not really. You can have this without the Intel ME, and you can have the Intel ME without having this.
Thank you.
So another thing, also, you don't need a TPM for this either. This is all implemented in the firmware. So you don't need to have additional TPM hardware in order to have secure boot. So even if you buy a machine without a TPM, it can still have the secure boot protocol provided. So we spent a long time talking to hardware vendors. We spent a long time talking to firmware vendors. We spent a long time talking to Microsoft. Red Hat last year joined the UEFI forum, so we have been going to meetings with all the hardware vendors and all the firmware vendors. Canonical are also members. I think SUSE are members again now. There was some, during the Novell SUSE period, there was some difficulty. So the Linux vendors have been involved with this, and we've all been trying to find a solution. So I was at the Plugfest here in Taipei last month, where we sorted out some final details of this. But when I say we here, I'm talking about Fedora primarily, and it's likely that Red Hat Enterprise Linux will have a similar solution, but so far, Canonical and SUSE have not said what they plan on doing. Debian hasn't said what they plan on doing, so I'm purely talking about our solution at the moment. Other people may have different preferences for their solution. Our solution, if we go back to the original thing, we're going to have a bootloader that is signed by Microsoft. Microsoft will grant access to the signing service if you pay VeriSign $99. VeriSign then verify your identity. VeriSign give you a couple of smart cards. Those smart cards give you access to the Windows signing service. And you can then upload a binary, and then you get emailed back a signed binary. And that signed binary is signed with a trusted Microsoft key that will execute anything on any system which has Microsoft's key installed, which is going to be basically every system. Inside that bootloader is going to be a copy of our public key. And that way you can have a binary that is signed by Microsoft, but which will then only launch Red Hat operating systems or Fedora operating systems. And the idea here is that we can then maintain control of the operating system updates we provide. We don't have to go to Microsoft and ask them to sign every single kernel update we provide. But it also means that anyone else can do the same. Any other Linux distribution can take the bootloader that we've produced, can swap our key with their key, can get it signed by Microsoft, and can then put that on a CD or a DVD or a USB stick, and then that will run on any system with Microsoft's key. And this means that we don't have any specific advantage. There's no situation in which a system will run us but won't run another Linux distribution. Anyone who's willing to go through the same steps as us will be able to run on those systems. And this is obviously controversial because we have to trust that Microsoft will continue signing our updates. And Microsoft obviously have the ability to revoke our binary signatures. They can blacklist our bootloader if there's a security issue. And given past history, there are obviously a lot of people who feel very uncomfortable with this, which I obviously can't blame them for. But there's no good solution that we'd be able to come up with, and this, of these solutions we found, seems to be the least worst. It's bad, but it's not as bad as some of the others. So I'm really sorry about that. So as I said, anyone would then be able to do the same thing. Distributions can take our code, even though the binary is going to be signed by Microsoft, the source code will be available. In fact, the source code is currently on GitHub. You can download our bootloader and run it on a UEFI system. It will then verify the keys before executing things. You just swap out your key instead of our key, and it will work just as well as it does for us. So I'll be publishing more information about that soon. There's a small number of features I still need to add to it before I consider it finished, but it's very nearly done now. It's only a small amount of code, except that we then have to link it against OpenSSL for the cryptography, which means the binary ends up being about 1 megabyte, which is unfortunate. But anyway, that's what we're doing. Now, the problem here, obviously, is that that's something that only works for the people who are willing to go out and give money to VeriSign in order to get a signing key. If I'm just a home user, and if I want to replace my kernel, so say I install Fedora, Fedora will have a Microsoft signed bootloader, but that bootloader will only launch Fedora kernels, will be signed the kernels. If you want to build your own kernel, you don't have our signing key, so the bootloader will refuse to launch our kernel. And you have two choices there. You can either turn off secure boot entirely, and Microsoft, the same requirements that say you must have secure boot also say you must be able to turn it off. The problem is that they don't say exactly how you can turn it off, and that will vary between firmware vendors, it will vary between system vendors. And it's difficult to document that. We have to say, well, go into your firmware, and you may have to hit different keys to get into your firmware. And once you're in your firmware, find something that says secure boot or words like secure boot, and then change it to disabled, or it might be off. Something like that. That's not particularly easy, but if you do that, then you can go back to running whatever you want. But if you want secure boot, say you do want to protect your system against malware being installed, then you can replace the keys that are pre-installed with your own choice of keys. Microsoft, again, guarantee that. They have something called custom mode. You can delete your keys, you can install new keys, and once you have your keys, then you own the chain of trust. We'll be providing all the tools that you need in order to generate a key in order to sign the binaries with your key. And then the only way anyone can run software on your computer is if they've got hold of your key, which means you're protected against pretty much anyone. Unless there's backdoors, you're even protected from Microsoft and the US government. Assuming there are no backdoors. So here we have a happy user who has installed their own keys, and it is the user's keys that are trusted. See how happy the user is. The user is very happy that only their software runs. We obviously like happy users, and we hope that everyone likes happy users. Things are actually a little more complicated than just thinking about the bootloader and the kernel. Obviously, if you load an unsigned kernel, then you can replace the kernel with something that is malware. So we only launch a signed kernel, but say once you've got the kernel, you then load unsigned code into the kernel. And that could be a kernel module, for instance. You load a kernel module, and then that kernel module could stop the kernel from executing any user space code, could then set up a bunch of entry points that look like an EFI interface, and could then read, say, the Windows bootloader off disk and execute it. And the Windows bootloader would then think that it's running in the firmware environment, but actually it's running in your fake firmware environment. And once it's there, you can modify it, you can break it, you can go back to having the entire boot process after that point compromised. You install your fake firmware records all your keystrokes. The user types in their passphrase to decrypt their hard drive, and you save a copy. And then later, you send that to a remote address, because obviously EFI has a networking stack. If you reboot, you can get network control and you can send that to anywhere you want to, and then you have the user's keystrokes. So in order to protect against this, we need to start thinking about ways of making it impossible for the kernel to be modified. Kernel modules are one part of that, but there are many different ways that a user can currently execute code in the kernel. For instance, if you have access to dev mem, you can just directly modify the contents of memory, and you could modify the kernel at runtime. So okay, we can disable dev mem. Then you have your graphics card, and your graphics card is able to do DMA. So you upload a command stream to your graphics card that says, please DMA this set of data to this address, and then your graphics card overwrites the kernel. So we have to restrict what your graphics card can do. And there's two ways of doing that. Well, we can do that with the IOMMU, but not all systems have IOMMUs. And IOMMUs often cost performance, and people dislike it when their expensive graphics card doesn't run at full speed. So we need to instead stop the user from being able to directly program their graphics card, which means we have to prevent user space from being able to directly access PCI configuration registers. And that also means that we have to restrict things like port I/O, in-B and out-B. We have to prevent those being started from user space. It used to be the case that if you were root, then that was game over. If anybody gained root access, then they could compromise your entire system. We're having to start thinking about protecting the kernel against even root. Root must not be able to modify the running kernel. And this is a big security issue. This is a lot of work to do this well. We have currently nowhere near enough people working on this, but it's going to be interesting to find solutions. That means that there's going to be some changes. And the biggest change that we're likely to see is that because we can't just load modules, modules are themselves going to have to be signed. And for a distributor, that's okay. Fedora can, when we build our kernel, sign all the modules that we distribute. But if you provide modules as a third party, then it's very difficult for anyone to do that. And we can't just give NVIDIA our signing key. And NVIDIA have the problem that, well, right now they give out a mixture of source and binary, and then the user builds that on their own system so that it matches the running kernel. So even NVIDIA can't sign something and then just give us the key, because the signature has to match the binary, not the source code. And so far we don't really have a good solution for that. We don't know how we're going to deal with third-party modules. But from a sort of high-level thing, since we're going to be locking down PCI access, since we need to stop people using their graphics cards to do DMA. That means that the traditional user space mode setting drivers that we used to have are going to have to be blocked. That means that any graphics support on Linux is going to have to be through kernel space mode setting, or KMS. And we have KMS support for NVIDIA, Radeon, and Intel, and we've recently landed KMS support for some of the server chipsets, like the MGA G200 that's used in various server chipsets, and the ASpeed, the AST that's again used in servers, and also KMS support for the Cirrus GPU that's often used in virtualization. So that means that we can provide kernel level support for all of these graphics devices, and we don't have to give user space direct access to the GPU, and that improves security. As I said, third-party drivers must be signed. We don't have a solution for that yet. And certain kinds of kernel debugging are going to be difficult or impossible with Secure Boot enabled. If it's any consolation, the same is true for Windows. If you want to use the Windows kernel debugger in Windows 8, you need to disable Secure Boot first. You need to reboot the system, turn it off, and then boot, because otherwise you could use the kernel debugger to modify the kernel at runtime. Now, is anyone here working on ARM platforms at all? Okay. Now, what I've been talking about so far is x86. For ARM, the situation is a little bit more complicated. ARM systems must have Secure Boot enabled. And when I say ARM here, I mean Windows 8 certified ARM systems. So the majority of ARM systems right now, this is completely irrelevant. The majority of ARM systems don't have EFI, and even if they do have EFI, they don't have the Windows 8 requirements, so this isn't a problem. But with Windows 8 supporting ARM, we are going to see some vendors providing ARM systems with UEFI booting Windows, and those systems must have Secure Boot enabled, and it must not be possible for the user to disable Secure Boot. And it must not be possible for the user to install their own key. Now that means that it's going to be possible for vendors like well, Red Hat, for instance, could produce a signed version of Linux for ARM and then have it run on these devices, because we could get our binary signed by Microsoft. We don't want to do that because we believe that the user must have control of their system, and we don't want a scenario in which a user can install Red Hat but then not be able to install a modified kernel. But it does not prevent, say, a company producing a dual boot ARM device that runs Windows 8 and Android, because they can do the signing themselves. Right now, we have no idea how big the Windows 8 ARM market is going to be. It doesn't exist at the moment. If it becomes big, this is going to be a problem. If it is small, this isn't going to be a problem. We'll find out in a year or so, I guess, maybe a couple. But until then, this does restrict freedoms for people, and we don't know for sure how much of an actual problem that's going to be. With luck, not too much of a problem. Anyway, that is, in terms of the content, what I wanted to cover. But it's a complicated subject. There may be bits that I have not explained very well. If anybody would like to ask any kind of question, I would love to answer them.
Yeah, you just mentioned that the Secure Boot must not be disabled in the ARM system.
Yes.
And why there is different policy between Intel architecture and the ARM architecture?
Why is there a difference between the x86 and the ARM? For the real answer to that, you would need to ask Microsoft, because Microsoft wrote those requirements. But we can make some guesses. Obviously, Microsoft dominates the x86 market. Almost, certainly at the consumer level, almost every PC sold runs Windows. That gives Microsoft a lot of power, and if Microsoft insisted that Secure Boot be enabled on all of these systems and there be no way to disable it, then that might cause them legal problems in certain places. right now, Microsoft have almost no influence over the ARM market. This would be a small number of ARM systems. But the other thing is that right now, the ARM market is already very associated with locked bootloaders. A lot of Android devices sold, for instance, have locked bootloaders. All the Apple phones and the iPads have locked bootloaders. And this is effectively the same. It's a locked bootloader. It will not launch anything that isn't signed appropriately. So Microsoft can say, we're not doing anything different to the existing market, whereas on x86, they would be changing the market. So I suspect it's partially for PR purposes, it may be for legal purposes. For the real answer, you would probably have to ask Microsoft, and I don't know that they'd give you the real answer. They might themselves give you something like I've just said.
My name is Philip. I come from Trend Micro, and I have worked as a BIOS programmer for years. I'm a little bit confused because although kernel-based attack is theoretically possible, is there any real-world example to illustrate how it can be? And as you know, a conventional boot sector virus does not run on the CSN end, and I doubt that there's any malware that pretends to be an UEFI driver and runs as a DC or runs as service.
At the moment, you're completely right. There is no real-world example of this. The reason that we are looking to lock the system down against the kernel-based attacks is that if we prevent the existing boot sector attacks, then malware authors have to start looking for new ways of attacking systems. And we want to make it as difficult as possible for them to do that. If it's easier for an attacker to attack a Windows system via Linux than it is for them to attack it via Windows vulnerabilities, then they'll use Linux. And then our keys will get blacklisted. And then our software will no longer boot, and that's bad. So we want to be at least as secure as Windows. We do not want Linux to be the easiest way of attacking Windows. And that's why we want to protect against kernel-based attacks. Right now, it's theoretical, but if we protect against it, we can attempt to keep it theoretical. Otherwise, there's a chance that it would happen in the real world.
You can talk about when we have loader, we only load the photo of overhead distribution. Does that happen only when secure boot is enabled? Or
yes, that's only while secure boot's enabled. If you disable secure boot, then, well, it will. I haven't finished writing that code yet, because I wanted to get the more complicated stuff done first. But yeah, once that is written, then it will, if secure boot's disabled, it will boot anything. We turn off all the validation if secure boot's disabled.
It may seem crazy, but I'm considering about a method that using virtual machine to boot a system.
Right. Virtualization, you could potentially get around this because you could launch your signed kernel, and then without launching any unsigned modules, you could go into KVM, or if you're using Windows, you could go into Hyper-V. And if you configure that appropriately, then you could boot quite quickly, automatically bring up the virtual machine, and then you could do PCI pass-through, and it would look like you're running on the real hardware. We've been talking to Microsoft about this. So far, Microsoft don't seem to think that this is a big problem. We don't know for sure yet. But that is the most obvious way of getting around this. And it may be that we end up having to disable virtualization when secure boot's enabled. And we hope that that won't happen, because that was obviously caused a lot of problems. That's kind of a limitation at the moment. And you could do that, and that is the biggest problem we have.
Did you get a chance to hear any comment from other governments than the United States?
We haven't even spoken to the United States government about this.
China government?
They don't let me speak to governments. I would probably say bad things, and yeah.
I mean,
in terms of whether we've heard feedback,
controlled by Microsoft as a commercial company in the United States is something
Yeah.
Doesn't make
but
sense.
I can imagine that some governments would have concerns about this. I have not been involved in those discussions. If people think that this is a potential issue, I really do encourage people to speak to their local authorities and make sure that they're aware of what's going on and that they're okay with this. This is right now going to happen. The hardware to do this has mostly already been produced. It's sitting in warehouses waiting for Windows 8 to be finished so that Windows 8 can be installed. And unless a miracle happens, this is what's going to be shipped, and Microsoft are going to be the only ones with their keys installed on most systems. So if any governments do have concerns, they should really do something very, very quickly. Otherwise, it's just going to happen. Okay, so I've got 2 minutes left, so if there's one more question.
So Red Hat is not going to have the Red Hat KEK onto hardware, right? So
Right, we will not have a KEK, which means, sorry, yeah.
So my question would be how without a KEK, the Red Hat will not be able to update the DBX.
Right.
So how does Red Hat see this kind of scenario, like a whole region of the
So we don't need to update DB because we'll be using the Microsoft key for booting, and then we'll have our own key built into the bootloader. If we need a new key, then we'll just put out a new bootloader version with a new key built into it. DBX, we will probably be coordinating with Microsoft on that. If we need anything blacklisted, we will tell Microsoft. And if Microsoft needs anything blacklisted, then we'll be taking their updates and we'll be putting those through our security update mechanism as well.
But the system will be only, let's say, Motorola, and it's not only because you won't be able to update the DBX.
We will update the DBX with any entries that Microsoft update DBX with, because if the Microsoft key is still there, then we will be able to use the Microsoft updates to update DBX. Through Linux, yeah. So we've been working with them to make sure that this is possible. If we want anything blacklisted, we'll give Microsoft
依据人事行政局总处公告，今日即刻停止上班，请各单位于下班前确认将内部不需使用之电源拔除，并确实将内部窗户关闭，以免造成不必要之损失。 依据人事行政局总处公告，今日即刻停止上班。各单位于下班前确认将内部不需要使用之电源拔除，并确实将内部窗户关闭，以免造成不必要之损失。
GPLD3 says you must give the keys out. I thought that. It turns out that's not what it says. You have to provide keys. You have to provide everything necessary to replace the component, including signing keys. If it's possible for a user to replace the component without your signing keys, then that's okay. If they can install their own signing key, that's sufficient. It also only applies to user products. And an operating system on its own is not a user product. If I hand you a CD with a signed grub on it, I can do that, and I don't have to give you any keys. It's only if that's installed on a system and I give you the system. Now, I'm not a lawyer. This is my understanding. If this is something you want to do, you should speak to a lawyer first, and don't just take my word for it. But my understanding is that it's as long as either you're just providing the operating system, or if the user can replace the keys, then you don't have to worry. If you sell a system with a signed grub, and it's not possible for the user to replace the keys, then you would have to replace the key. You would have to provide the keys. Speak to a lawyer. Don't trust me. Do not base business decisions on what I've just said. And if you get sued, it's not my fault. So I think I'm out of time now, but feel free to talk to me, ask me any more questions at any point during the day. And thank you very, very much for inviting me here. It's been a pleasure.